Okay, this is another part of our systems packet, and this was on page 21, at least if you have the current version of the packet. So what if we want to use elimination, but we don't have a common coefficient? So right before this, we learned about using elimination, but we could simply either add or subtract the two lines. If I try now to add or subtract the two lines, nothing will eliminate. So if there aren't common coefficients to start with, then we can multiply. It's legal, right? It's the same reason we can solve an equation. We can multiply one or both equations to create common coefficients. And we'll say a pair, because you're not going to, I mean, it could happen, but it's going to be a special case if it does. You don't really want it to be both, you just want either x or y. And I would suggest that you go ahead and create those common coefficients to be opposites. Okay, so not just 4 and 4, but like 4 and -4, 2 and -2. Because then you don't have to worry about subtraction. Then you can always treat it as addition. It can be the x or the y, but it's best if you find the way that you have to multiply the least. Because each time you multiply, you're multiplying by every term, so it's 3 chances to make a mistake. So if I can just multiply one line instead of 2, I'm lessening my work, and I'm lessening my opportunities to make mistakes. So I can make this 1x the opposite of 2x by multiplying the top line by -2. Sometimes people think, well, where do you get -2? Well, because 1 goes into 2 2 times, and then I want them to be opposite signs. This is perfectly legal that I can do this, perfectly legal in math, as long as I multiply every term all the way across the equation. So including that 6. So I multiply everything all the way across by -2. The second equation in this case does not need to multiply. If I multiply by something, then I'm just going to be screwing things up, and then my x's won't be opposites. After I've done that, then it's like what we were dealing with before, because now we have common coefficients. So I have a pair of opposites. So -2, +2 cancel out, they're gone. There is no more x. -13y is equal to -13. We divide, so y is +1, and once again we still need to plug it in. Now, because we could have made a mistake distributing, also the numbers will be bigger if we use our new equation, so use one of your original equations. If everything has been done correctly, you should be able to get the same answer from your new equation, but again, the numbers are just going to be a little bigger, so it's going to be typically easier to use one of your original equations. So I plugged in 1 for y, so x plus 3 times 1 is 6. Now I'm going to take that 3 away from 6, and x is 3. So 3, 1 is my solution. And if I want to check, 2 times 3 is 6. Subtract 7 times 1, which is 7. So 6 subtract 7, ding, 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 is -1. So life is good. It may not be the x that you can eliminate most easily. It might be the y. So in this next problem, 2 doesn't go into 9, so I'm going to look at my y's. 1 does divide into 3, so I'm going to multiply my second line this time by -3. So second line by -3 all the way across. You can pause me and try it on your own, see how you do. Make sure you take it all the way across. Top line doesn't need to change. Sometimes people will write their new one underneath and then go the top and the bottom. I just prefer to see my things nicely lined up, and I find people make less mistakes that way. So in this case, it's the y that eliminates. 9x -6x makes 3x. 12 and -15 is -3. Divide by 3. And x is -1. And you know the drill. After you have one of the variables, you need to plug it in to find the second. You could plug it into the top or the bottom of the originals. I just typically go with the top. Nothing magical about that. It's just what I do. So 9 times -1 is -9. Got my two-step equation now. Add 9. Divide by 3. And y is 7. 2 times -1 is -2. Plus 7 is 5. So in case you're not sure what I'm doing there, I just put both numbers into that second equation to check to be sure that it's right. And I just kind of ran that through doing some mental math. If you happen to have used the second equation to find y, then you would want to be doing the check with the first equation. You're not really checking much if you just check the same equation you just plugged it into, because there are infinite pairs of numbers that make that equation true. But there's only one pair of numbers that make both of these equations true, because these two equations would intersect in just one point if we graphed them. So, got one more challenge. The next challenge is that sometimes the x and the y, like I can't make either one of them match. That's not a no solution situation. That means we have to multiply both equations. So let's take a look at one of those. Okay, if you have my current handouts, if you turn the page to number 8, and if you don't have the handouts, obviously you could be writing things down. I guess it's kind of late to say that now, but all right, so now 3 doesn't go into 5. Like, I can't multiply 3 by a nice whole number and make it the opposite of 5. I also can't make the 3y the opposite of 4y by multiplying, not by a whole number, and I don't want to deal with a fraction, so nope. So we're going to have to multiply both equations. Now, it is your choice whether you want to multiply both equations to eliminate your x or eliminate your y. It's really very much the same amount of work in this case, and both numbers are around the same size, so not going to be a big advantage of one way or the other. I'm going to choose to eliminate my x's just because I find for my students that like the 3 and the 5 are right there on the edge, so this is just a little more obvious to them since they're right there on the left side. So when this happens that I can't just multiply one line, then I'm going to switch my coefficients. You might think, what? I'm going to switch them to decide what to multiply by, because 3 times 5 would be 15, and that would be a common multiple for the 3x and the 5x. And in this case, it's also the smallest one I could come up with. But even if it wasn't the smallest, it would give me the correct answer. I might just have bigger numbers in the middle. So the top line is going to get multiplied by 5, and the bottom line is going to get multiplied by 3. Now, one of those two lines I want to be a negative so that they're opposite. Doesn't really matter if I put the negative with the top or the bottom. In this case, I'm going to choose to put it with the bottom. Do not put it with both, because then you would make them both negative and it wouldn't cancel out. So now we're going to multiply all the way across that top line. Remember, we're distributing it all the way across. So 5 times 3x, then 5 times 3y, then 5 times 9. If you forget that step, things go poorly. Now, bottom line, everything times negative 3. So I have negative 15x, negative 12y, and negative 30. So now, even though I multiplied both, once I have that, then I'm back to the same process as with our very original elimination problems. Now, if you get to this point and you look at your two lines and there is not a pair of opposites, please don't try to keep going, because something is wrong. You didn't multiply by what you needed to, or negatives or something. So the whole purpose of the multiplying step is to create those common coefficients, preferably opposites, so we don't have to use subtraction, we can just add. So here we go, 15 and negative 15, 0, x, you are eliminated. 15y and negative 15y, 3y. 45 and negative 30, 15. Then we can divide by 3 to find that y is 5. Remember, we're going to take that y back and plug it in to one of the two original equations where the numbers are a little smaller. So 3x plus 3 times 5. And if you just kind of like, okay, I know that 3 times 5 is 15, and you just wanted to go straight to writing 3x plus 15 is 9, perfect, wonderful. I just don't want people to like watch this and think, where did 15 come from? So there you go, 3 times 5 is 15. Take away the 15 from 9, right? Because I got to take it away on both sides, so I got rid of it on the left. Now I've got negative 6, divide by 3, and x is negative 2. So negative 2, 5. So far so good, I hope. All right, one more example. All right, welcome back. There we go. Let's try number 9. So take a minute. What do you think you should multiply by? So pause me and write down what you would multiply. I will tell you you need to multiply both equations. Now, notice this time I just chose to put my negative with the top line. If you put negative 5 and positive 7, also perfect. I also want to point out, if one of them was already negative, then you wouldn't want to use a negative, because then you would be switching it back to positive or switching the other one to negative, and they would not be opposite. Right? So that switch method, again, I'm just switching those two coefficients. As you start multiplying, then hopefully you see y. So when I just think about those x's, right, and then those will eliminate. But please remember, you have to multiply all the way across. So a couple more thoughts. on problems 10 and 11, even though I see x's, y's, numbers, the equal is not in the same place in number 10. So you do not want to just jump in and start trying to do elimination while the x's and y's are on different sides of the equation. So if I wanted to do this with elimination, I would want to move this guy over here first, and he would become this. And then, with this new equation, now I would multiply the top line by 5, and this bottom line by 2. And notice I would not use a negative with either one of them, because the x's on top are positive prior to being multiplied. The bottom ones are negative. I want them to be opposite. Right? So I hope this was helpful. For the assignment that followed this page, I assigned 1 through 10. We did not do number 11 and 12 on the assignment page that follows this. All right, hope to see you soon.